next speaker is Fiona Harrison from Caltech. And she, as many of you probably know, is the PI of the NuSTAR mission that was launched last June, and she will tell us as soon as they find the presentation about the NuSTAR results on active galactic nuclei.
Try that. Let's see if it works. Yeah.
Hey, yeah.
Okay, well, one of the first things that I did when I came to Caltech as a postdoc is I went to a symposium in honor of Maarten. It had to do with luminosity functions, as I recall. And I remember being odd to be in the same room as the discoverer of quasars. So I'm very honored to be asked to give a talk here today. And what I'm going to tell you about, originally the title was AGN with NuSTAR, but in honor of Maarten, I've changed to quasars with a little discussion of AGN with NuSTAR. So if you're not familiar, NuSTAR is NASA's most recent astrophysics mission. It's a small explorer, so the smallest scale mission that NASA does. And it is a PI-led mission, and we're in our baseline mission phase. We launched about 1 year ago. So I'm going to give you some concrete results and then a flavor for what's to come in the near future. So just to put NuSTAR in perspective, NuSTAR is a high-energy X-ray mission. So compared to Chandra and XMM, which have been the premier facilities working between about 0.1 kiloelectron volts and 10 kiloelectron volts, NuSTAR operates between 3 kiloelectron volts and 79 kiloelectron volts. So it's expanding the bandpass with which we have to make sensitive studies of the X-ray universe significantly. So, of course, it's not the case we've never had high-energy X-ray observatories. Observatories like the Swift-BAT and Integral, based on basically coded mask techniques, have been fabulous for studying bright transient sources and time-domain high-energy X-ray astronomy, but they're limited by the fact that the signal is encoded over a large detector area. And so each pixel in the sky takes a large background into account. And in this region of the spectrum, we're very dominated by internal detector backgrounds. So NuSTAR is the first focusing telescope, the first telescope to be able to take a large collecting area and focus it down onto a small area in the detector, reducing backgrounds by factors of thousands and improving sensitivity by more than 100-fold relative to anything that we've had in this bandpass before. So let me just show you the collecting area of NuSTAR compared to Chandra and XMM in a quantitative sense. So this is 10 keV, 100 keV, and this is the total collecting area. And you can see relative to Chandra, XMM, Swift, and Suzaku, which have cutoffs in their sensitivity, abruptly sort of between 7 and 10 kiloelectron volts. NuSTAR extends a sensitive collecting area all the way out to 79 keV, where there's an edge in the response. And the consequence is that compared to something like Integral or Swift-BAT, we can go from sort of millicrab, never mind the units, just for the optical astronomers, remember smaller is better. So we go from something like a millicrab to a microcrab. So a very significant improvement in sensitivity. So what I want to do in this talk is provide a high-level overview of early results. And many of NuSTAR's results stem from the combination of sensitivity and broadband X-ray coverage. So especially combined with XMM, Suzaku, and Chandra, we're getting the very first high-quality X-ray, broadband X-ray spectra of AGN and quasars. And so for background, especially for the students in the audience, I just want to remind you what the components are of the broadband X-ray spectra of Seyferts and quasars. So there is something we call the corona. We don't know much about what it's associated with. It could be the base of a jet or something to do with the inner accretion disk, but it's a hot electron plasma which upscatters photons from the accretion disk, and the result is a hard X-ray continuum which can both shine down on the disk and reflect from it, also reflect from distant matter, giving us features in the X-ray spectra. And also, in many systems, there's a jet, shown here, which can be a source of X-ray emission. I'm going to limit myself to discussing objects without strong jet emission, but I would like to advertise the poster of my student, Mislav Balakovic, who has some results from observations of Markarian 421. So here's what the spectra look like. So we have this direct continuum from the corona, and what's going to be important for this talk is it's typically characterized by a fairly steep photon index, gamma of 2. So that's something that's roughly flat in nu f nu, all right? And then superimposed on that, we can have reflection from either distant material or the accretion disk, which looks characteristically like this spectrum here. You get prominent iron lines. Iron has a high fluorescence yield. It is astrophysically abundant. And then also a Compton reflection hump, which peaks in the NuSTAR band. You can see between 10 and 30 kiloelectron volts. And of course, the strength depends on geometry and the density of the material. But at any rate, these are the basic features that are going to be important. I also want to point out something. This is just following up on what Günther said this morning, that the X-ray band is somewhat unique for being able to measure column densities of material, because you get a strong cutoff with X-ray energy that depends on the column. And I just want to orient you to the columns now that we can extend to with NuSTAR. So this is energy, and this is flux in nu f nu. So I've taken my steep power law and flattened it out here, but you can see there's, in the XMM and Chandra bands, you can easily measure columns in the local universe of 10 to the 22, but once you get beyond 10 to the 23, the entire soft flux is strongly attenuated. NuSTAR can extend column measurements out basically to the Modley-Compton-Thick regime, after which the entire X-ray continuum gets suppressed. And so this is just some background that's going to be important for understanding our results. And so I'm going to start with the result on the nearest quasar. We've been talking about things at high redshift, so let's now see what we can say about Markarian 231. So Markarian 231, besides being the nearest quasar, it's a broad absorption line quasar, which means you see these very broad absorption lines in the optical UV that are indicative of fast outflows, right? So the generic model for these broad absorption line quasars is that you have a line-driven wind, and that's what, and because we're looking at fairly high inclinations, we're looking at the disk wind through this wind, and that's why we're seeing the absorption lines. But here in the center, we have a very powerful quasar, and in order to, these winds are line-driven, and in order not to completely over-ionize the material, you have to somehow shield this central source to avoid this over-ionization. And so a shielding gas or failed wind is invoked in order to do this. Now, this fits in with the general observation that many of these Bal quasars are X-ray weak, and it's been postulated that they're X-ray weak in the soft band because of absorption due to this wind. And so we looked at Markarian 231 because it had been detected by the Suzaku pin, which is a non-focusing hard X-ray detector, and by Beppo Sachs in the hard band. And so the theory was that what's happening is in the hard band, you're punching through this wind, and suddenly we thought, okay, we're going to get a booming detection in NuSTAR, and we're just going to measure the column of this wind. So here are the Beppo Sachs points in black and the pin points in green, here's the NuSTAR spectrum. All right? So we don't see any evidence that we're punching through a wind, all right, at all. And in fact, it now appears that the Sachs and Suzaku results are just contaminated. They have very large fields of view. They're non-focusing. There are many sources in the field of view. So this flux isn't actually from Markarian 231. So what's interesting about this? Well, so you can model the broadband spectrum. It's a bit complicated because, as many of you know, it's also a ULERG, and so you have to account for emission from HMXBs and star formation. But if you do that, you find that it's only moderately absorbed, about a column of about 10 to the 23. There's no Compton hump, all right, so there's not much a dense material, and the spectral index is quite hard. Instead of 2, it's about 1.4. So our conclusion, basically, is that absorption can't explain the X-ray weakness. This object is somehow intrinsically X-ray weak by a factor of 100, all right, relative to what you would expect. And you may be thinking, well, okay, what if it's just very Compton thick, many 10 to the 25, and you're just suppressing everything? Well, there's very little room for that because we have excellent constraints from Chandra, which isolates the nucleus. And if it were truly Compton thick, we would expect more scattered emission in the Chandra band. So we're left with the conclusion that the nearest Bell quasar is just really weird. It's incredibly intrinsically X-ray underluminous. So maybe that's just a coincidence. So we thought, actually, that before we looked at Markarian 231, as part of this program, we said, well, let's do a sample of low redshift Bell quasars. And just what we'll do is we'll measure the range of columns, and we'll try to understand the distribution of this failed wind. And in fact, for the 2 that we observed, they're also apparently either extremely Compton thick or very intrinsically weak. And so this shows you alpha OX versus 2,500 angstrom luminosity. This is just a distribution, typical distribution for quasars. Here's Markarian 231. Here's PG 1700, right, which is another one in our sample, also very intrinsically X-ray weak. And there's another source that we've looked at now that lies here. So, so in the bigger picture, I mean, this is kind of interesting. We're finding these very intrinsically X-ray weak sources, Bell quasars. But so what's the implication? Well, if the broad absorption line nature is just largely an indication of an inclination effect, and a significant fraction of absorption line quasars are X-ray weak, this has implications for how for inferences of obscuration in the deep fields, right? Where you're just assuming an optical to X-ray or infrared to X-ray intrinsic flux distribution of a large fraction are intrinsically weak. This will change your conclusions. So I actually want to point out, I was at the same conference last week in Italy as Lewis was, and this whole discussion of these Bell quasars has now sort of encouraged theorists to go look at models where actually the failed wind can quench or alter the coronal emission. Okay, so let me turn to obscured quasars and the NuSTAR surveys of obscured quasars. Now here, things are very much in progress. So we're only halfway done roughly with the surveys. We're actively analyzing the data. So what I can do is just give you motivation for the surveys and some initial results that show you the promise of what's to come. So Günther's given a nice motivation for this work, which is that there's a significant number of obscured AGN required to explain the shape of the X-ray background. And so the goal of the NuSTAR surveys, given what I've told you about what we can do with broad bandpass for low redshift sources in constraining the columns, is to constrain the evolution of obscuration sort of between 0.1 and 2 redshift. So we're doing this through a combination of blank fields, famous fields like Cosmos and ECDFS, and then also taking a sample of slow and obscured quasars, where we don't actually have measured columns from the X-ray, all right, but we have reason to believe that they're highly obscured based on the O3 to X-ray flux. And then also, we're trying to understand the spectra, broadband spectra, by looking at a local sample of Seyfert's. So let me start by telling you a little bit about what we're finding with the Sloan selected obscured quasar. So the sample was selected to be redshift of about 0.5, and with evidence for significant obscuration based on the 2 to 10 to 0.3 ratio, indicating of a factor of 100 or more suppression of the X-ray band, presumably due to obscuration, although the BAL results have me a little bit wondering about that now. So we have 3 that we've looked at so far, and 1, we got a detection in the hard band, and based on the band ratio, it does in fact indicate a moderately Compton thick source of around 10 to the 24. And then the other 2, we're finding very strong suppression of the hard band emission, right? So basically non-detection in the NuSTAR band, but detection in the soft band, showing that these are indeed extremely Compton thick systems, 10 to the 25 or more. And so when we have a large sample of these, then we can actually, for the first time, say something about the range of columns in these, this sample of obscured quasars. So in the extended Chandra Deep Field South, again, we're still analyzing the data and looking at the distribution of sources. But I want to illustrate the power of the hard band by giving you one example, which is this source here, NuSTAR J033, whatever. It's also been detected by Chandra and XMM. But by Chandra and XMM, it wasn't uniquely identified as a highly obscured source. Right? It has a flat, soft X-ray spectrum, but was not identified as extreme. But when we go and look with NuSTAR, we see that in a broadband, including very hard X-rays, we get a detection, whereas we don't in the soft band. So this is indicating by this band ratio that it's identified as a highly obscured quasar. And in fact, if you model the spectrum, you get NH of 5, 10 to the 23. Now, we don't have a redshift. We have Keck and VLT time coming up to do follow-up. But there is a redshift. We do detect, there is a detection of an iron line and an iron edge, which puts this at a redshift of 2. And the luminosity is very definitely in the quasar regime. But what's interesting about this is that with the broad NuSTAR band, we can constrain the reflection fraction, which we find actually fairly prominent reflection, right? And now that's very interesting, because in most synthesis models for the X-ray background, it's assumed at these high luminosities that the reflection, that's the contribution from that broad Compton hump, is essentially 0 or very small. So we're finding even in luminous systems that you can have prominent reflection. Of course, that will change all the conclusions from the synthesis models of the X-ray background. Now, I want to say another part of our survey is to look at the brighter nearby Seifert galaxies that have been detected all sky with the BAT, which has a very wide field of view. So it finds very bright nearby objects. But what's relevant here is for the first time we can actually get broadband X-ray spectra, and we can ask the question locally, what's the fraction of objects that are both highly obscured and have prominent reflection? And again, this will feed back into models that try to explain the X-ray background. And I just want to show you the sensitivity advance. This is at one of these BAT AGN here. That was a 5 sigma detection in 54 months of BAT in a 15 kilosecond NuSTAR observation. You can see we can get a highly statistically significant spectrum. Here's another example of a source where we see that it's actually completely dominated by Compton reflection, this prominent iron line and Compton hump. So when we synthesize all of this, it'll be another important ingredient for trying to understand what populations to put into modeling the X-ray background. Okay, so I want to conclude by just saying something about broadband studies of Sept galaxies. This is a place where NuSTAR, combined with XMM and Chandra, is turning out to be particularly powerful. And I'm going to illustrate with one example of an object we looked at, NGC 1365. And what we were actually looking for, we did some observations jointly with XMM. And in this source, very interestingly, there are clouds that are sort of moderate columns that obscure the line of sight on day time scales. And these are thought, at least some of them, to be absorbing clouds perhaps associated with the broadline region. And so by studying the obscuration over time, we can study the shape and the column densities and properties of these clouds. And so we were, this is why we originally did a set of 4 observations. And you can see this is the XMM data, this is the NuSTAR data. So what this dramatic variability here is the source basically going from obscured to completely unobscured because of these clouds crossing the line of sight. And so we can study the nature of these clouds. But what NuSTAR, the advance that NuSTAR has brought is both the ability to study these over a wider range of columns, but also the opportunity to study the reflection component off the accretion disk. So for these wildly different absorbing states, I have to say it's really awesome to see this wimpy Sept basically piled up in XMM, first time ever in this state. But if I basically model out the absorption and plot the residuals to the continuum, all right, so residuals to the power law, what we see in NuSTAR is the reflection component. And what we see, we note there's an extremely broad and prominent red wing to the iron line and a very prominent Compton reflection, which can only be explained if this is reflection off the inner edge of an accretion disk and these very broad wings and dominant Compton component is caused by the fact that the accretion disk comes very close to the innermost stable orbit for a rapidly spinning black hole. As you recall, if the accretion disk is prograde, orbiting in the same direction as the black hole spin, then for maximally spinning black hole, the accretion disk can come as close as 1 RG, whereas for a hole that's not spinning, 6 RG is the closest the ISCO can come. And what's really dramatic about this is we get exactly the same reflection spectrum and features, spin, inclination, everything, over this vastly different range of absorbing states. So the other thing that is new with NuSTAR is for the first time we're able to put good constraints on the nature of the corona. So I mentioned the corona, it's really probably one of the most poorly understood features. We really don't know what it's associated with. We know there are microlensing studies that suggest it's compact. The reflection spectra suggest it's compact, but we really don't know much about it. But other than you have a Comptonizing distribution of electrons that's upscattering optical UV photons. But if you have basically thermal electron distribution, you should get a cutoff in the broadband X-ray spectrum at a factor of 2 to 3 times KT, and depending a bit on the optical depth. And if you can measure this unambiguously with high precision, then you can say something about the optical depth and nature of the corona. And for the first time, we've been able to do this. Previous indications of a cutoff with Beppo-Sachs and other instruments have been very degenerate with the amount of reflection that you assume, and also have had extremely large error bars, like 100 keV plus or minus 75 for the cutoff. We're able to now get a very tight constraint on this. And in for example, IC4329A, we get an electron temperature of 50 keV with an optical depth of around 1.5. So we're extending this to more sources like MCG5 2316. So these broadband spectra are enabling us to really put physical constraints on components of the broadband of the emission in sieverts. So I just want to point out in closing, I have 15 seconds left, there's lots more than just quasars and AGN. Everything from magnetars and rotation-powered pulsars, X-ray binaries, where we're getting beautiful reflection spectra, we're able to do similar make similar constraints on the spin of black holes in those systems. And so there's lots more that we're doing that I haven't talked about. You can look at the website to see what we're looking at. And so in summary, things are working well. We basically achieved the design sensitivity, and we're providing new probes of obscured quasars in the physics of Sept galaxies. We are, I should say, even though we're in the prime mission phase, if you're an X-ray astronomer or aspire to be an X-ray astronomer, we are offering 1.5 megaseconds of time joint with XMM in the upcoming AO, even before the end of the baseline mission phase. And we've even given you analysis software with which you can analyze the data. Thank you.
Okay, time for a question or two. Burning question. Yeah.
So I have a question about the impact on the population of quasars is inferred if there's really higher reflection fractions, like you said, that you had this one case that are approximately 1 to the square. So what does it do to the inferred population of AGN of the obscure fraction explaining the Caltech?
Yeah, so just qualitatively, what it'll do is it'll reduce the number of highly obscured systems that you require to explain the background, because you can explain more of that basically hump with reflection.
I think there's a redshift too, though. If they're at high redshift, it's a problem because then it's the wrong energy, isn't it? I mean,
Yeah. Okay. So
40 keV, and if you move it to redshift 2, it's
right. So we're talking mostly about
so it still should
lower
be
redshift. Right, lower redshift. But we think most of it, the emission is.
Yeah, the example you had was redshift 2.
Yes, that's true. That's true.
Is there any tension with other estimates of the obscure?
We don't know yet. We're still, like I said, we're still completing the data collection. So I would expect the first papers, though, to come out this calendar year. I hope.
Okay, let's thank Fiona again.